Hello all, in this lesson we will be studying friction. Specifically, there are two different kinds, both static and kinetic. This is the bookwork we'll be doing with this lesson, but we'll do that in class. And please copy down this aim on a separate piece of paper, which will be filed under classwork in your binder, and watch this video. So based on what you saw in the video, I want you to consider the following questions. Why can't the kittens run up the slide? What factors influence your answers from above? And then also interpret the diagram to the left. This time, I would like you to answer these questions on a separate piece of paper underneath the aim. All right, so friction. Friction is a force that opposes the motion of two objects that are in contact with one another. In other words, when you are able to determine which way an object is moving, friction is the other way. Simple as that. So what causes friction is actually sort of interesting. If you were to zoom in on the surface between these two very smooth looking blocks, you would actually find that the surfaces are very jagged. It's as these points pass over each other when one is going, let's say, this way, and the other, let's say, is going this way. When those points pass over each other, they're going to create drag, which we would call friction. It's going to be symbolized with the symbol FF, and it is dependent on another kind of force, Fn. Fn is going to be the force that is perpendicular to the surface and pointing away from the center of the Earth. So if I were going to use that idea on this particular block, I would say that we have Fg, or the weight of the block, pointing down, and an equal force in an opposite direction is the force that this block is putting on this one. So that would be termed Fn, or normal force. It's going to be the exact same value as the weight, so I'll say equal. It'll just be in the opposite direction. We'll also be using the equations Fg equals mg in a lot of these examples. So for here, I want you to draw a free body diagram of a box on a table. Draw and label vectors for a force pushing to the right, a frictional force, a normal force, and a weight. So I'll do that for you. Here's my box, and we need a force that's going to the right. I'm going to call that one Fap. That's the applied force. And the frictional force is going to be equal in size to the applied force if the box is moving at constant speed. I'll get to more about that later, but let's say that the box is not accelerating. I'll just write that in. Then that means that I'll need an equal size arrow. That's a bit long, but we'll pretend it's equal. And this is the frictional force. The weight is going to point towards the center of the Earth, always. That's Fg. And equal in size to that one will be an upward force, Fn. So the Fn should be equal in size to the Fg, and the Fap should be equal in size to the Ff. So equilibrium is when an object is not accelerating. And that's because when an object is in equilibrium, its net force, meaning the sum of all the forces, is 0 newtons. So I'm going to pause the video now, and I would like you to choose which object, A or B, is in equilibrium based on these notes. If you selected object A, you were correct. It's in equilibrium. And the reason is because looking at object A, Fn and Fg are equal in size, so they'll cancel each other out. Also, the Fap, I'll just write in app here. The Fap is equal in size to the Ff. So overall, the Fnet is going to be 0 newtons in cart A. So that means that cart A will be moving with constant velocity as well. Constant velocity means no acceleration. And you would not have acceleration if Fnet is 0. And the reason for that is because F equals ma. So if Fnet is 0, whatever mass is, it doesn't matter. A would have to be 0. Now the third question asks me which object accelerates, and that's going to be cart B. And it's going to accelerate in the direction of the net force. The net force, I can tell you, is going to be in this direction. So basically, the normal force in this one is canceled by the weight. I can tell that by the size of the vector. But the difference in size of vectors of Ff, the frictional force, and Fap, those are clearly different sizes. So I can tell you for sure that it's going to accelerate in the direction of Fap. So I would just say, in which direction does it accelerate? I would say same as Fnet, which is in this diagram to the right. And that also answers why, because it's going to be the same as Fnet. So in this slide, I'm just going to introduce you to the friction equation that we'll be using this unit. We have Ff, frictional force, which measured in newtons. Mu is called coefficient of friction. You will find this on your reference table, actually on the very first page, bottom right-hand corner. It'll be called approximate coefficients of friction. And Fn is normal force. So hints to help you just early on, Fn is almost always equal to Fg. So basically, if the object is not falling, then Fg and Fn are the same, which means that you can use the equation Fg equals mg to stand in for Fn. And frictional force will also be equal to something sometimes. Frictional force will be equal to the applied force in the event that it is not accelerating or that it's moving at constant speed. So either it's at rest or it's moving at constant speed. Both of those things mean not accelerating, and that means that the applied force is equal to the frictional force. And the logic behind that, by the way, is that if it's not accelerating, then Fnet is 0 newtons. And that would mean that there's no acceleration. So if Fnet is 0, there's no acceleration, which means that the applied force is equal to the frictional force. So sometimes it's straightforward, but sometimes they'll give you this information and you'll put it in for Fn, and sometimes they'll give you this information and you'll say that Fap is equal to Ff. Also on this slide, imagine that you have like a book or something that is 4 centimeters by 6 centimeters by 10 centimeters. Let's say that you put it on, and so it has like 6 different faces on the book, and they're all different sizes. Like there's a wide side and a skinny side and all that. The frictional theory says that no matter which side of the book is resting on the ground, whether it's like a small side or a large side, the amount of friction will be equal no matter what. So that's what all of this text is saying, is that no matter what part of the book is resting on the table, so to speak, when you slide it, it's going to experience the same friction. So there are 2 different kinds of friction, but we will use the same equation, that is Ff equals mu Fn. We'll use the same equation for both, but the two types are called static friction and kinetic friction. Static friction is the force that opposes the start of motion. So if the object seems to be at rest or it's not moving yet, you should be thinking about static friction. But we also have kinetic friction, which is the friction that exists between two objects when one is in motion. So if the object has already begun moving, we would use kinetic friction. The only real difference between those two is going to be right here with my value for mu. Oh, I forgot its little bib. So mu has two different kinds. So you're going to have to look on your reference table at the approximate coefficients of friction, which is at the bottom right of page 1. And you'll see that there's two different columns, a kinetic side and a static side. So whenever you're looking on your reference table to gather your value for mu, you'll need to either find a static mu or a kinetic mu, and that'll all be based on the context of the question. So you have to use reading comprehension skills to figure out if the object is moving or if it's still at rest. If it's still at rest, then use the static mu, and if it's in motion, use the kinetic mu. Fun fact is that the kinetic mu is always less than the static mu. I have an example here. Kinetic friction for copper on steel is 0.36, and static friction for copper on steel is 0.53. And that's not an isolated example. That will always be true. Another one, let's say rubber on concrete, dry. The kinetic is 0.68, and the static is 0.90. So that's mu k and mu s. So that is going to be true for all of these guys. So I'm using a free body diagram to explain some of these concepts here. So I'll zoom in on the first one. This one is saying that the normal force, which is up, is equal in magnitude to the weight, which is down, and also the applied force is 4.2 newtons, and the frictional force is also 4.2 newtons. I can also tell you that this particular object is not yet in motion, as we've used a static frictional force here. And in the next diagram, it is similar, but in this case, the difference is that this is kinetic frictional force. Okay, so these two are equal, just so that you see that, but the applied force and the frictional force are still equal here. So that means that there is no acceleration for this guy, or not even for the first diagram. So there's no acceleration because F net is 0 newtons. So I know that, and I also know it's kinetic. And this is a neat example. The frictional force for kinetic friction is 3 newtons here, which is less than the previous example, which was 4.2 newtons. So that should be something that's sort of obvious now, because objects that are in motion will always experience less friction than objects that are not in motion. Static friction is always higher than the kinetic friction, as long as it's wood on wood and wood on wood, as long as the surfaces are similar. Also, I was going to just point out that you have no acceleration in both cases. It's just that this one is not moving, and this one is moving, but it's at constant speed. On this slide, I'm going to teach you how to determine the value of mu when you're given the applied force and the normal force. So with just a little bit of algebra, you can isolate mu if you do applied force over normal force. So I'll start solving from there, knowing that mu is F over Fn. And the applied force F in the first diagram is 4.2 newtons, whereas the normal force is 10 newtons, which means the value for mu is 0.42 with no unit because the newtons cancel. Now, if I do that again, mu over Fn for the bottom diagram, let's see, F over Fn, excuse me. The applied force in this case is 3 newtons. And the normal force in this case is 10 newtons, which means that 0.30 with no unit, because the newtons cancel, is my value for mu in the second diagram. Now, this should not be confusing that they're different, because the first one is a mu s, or static coefficient of friction, and the second one is mu k, or kinetic coefficient of friction. And mu s will always be larger than mu k. So down here, why don't the coefficients for static and kinetic friction have units? It's because F over Fn yields no unit, because they're both measured in newtons. We're going to use graphs on this slide. So if you can remember that mu is F app over Fn, then you're off to a good start. So basically, we're going to show that the slope of the line on this graph represents either mu k or mu s. So we're solving for mu. Now, when we do slopes, we're really doing rise over run. The rise in this case is the frictional force, and the run in this case is the normal force. Now, normally I say that mu is ff over fn, but we're going to use this equation instead, which is that mu is f app over fn. The reason why this works out is because if this object is moving at constant speed, then f app will be equal to ff, frictional force. So every time I see a frictional force in the equation right here, I'm going to instead, I'll write f app, and I'll leave the fn alone. And the reason that I'm stopping here is because we have f app over fn, which is the same equation as this. So if mu is f app over fn, and f app over fn is f app over fn, then ff, friction, over normal force is the slope. So that means the slope is going to be giving you mu. So in the second little piece, we have it's just saying that we have a wooden block on a wooden table, and how do we know that for sure based on this graph? I would just point out that we have this lower line, which is kinetic friction, and the higher line, which is static friction. And you know that static friction is always larger than kinetic friction, so then the slope here should always be larger than the slope here. Always have your static friction higher than your kinetic friction. But when we just calculate this slope, we'll get the value for mu static. So it's a rise of 10, which is this distance, and a run of 24, which is this distance, and that gives me 0.42, which if you look on your reference table, that's the static frictional coefficient of friction for wood on wood. And for the lower line right here, the rise is going to be 4.8 and the run is 16. So 4.8 over 16 is giving 0.30. And in both cases, the mu s and the mu k match up with the reference table values for wood on wood. So you know that it's definitely a wooden block on a wooden table. All right, guys, this slide is pretty important, and one of the things that is upsetting about this particular slide is that it does involve a little bit of equation that is not on your reference table. I'm going to write those equations in for you now. Okay, so I've wrote in two equations, one of which will almost never help you solve any question, and one of which will help you solve many questions. Blue is the one that's very, very important. Okay, so here goes. You have an object like a box of mass m, and you have an inclined plane, and you also will have an angle that the inclined plane makes with the horizontal. We'll call that theta. Now, basically, there are some forces here, And you can make a triangle that looks like this. So this guy right here in black, that's FG. That's the object's weight. And it's always pointing straight down towards the center of the Earth. So the object's weight is always pointed straight down towards the center of the Earth. And you can also remember from statics that we can split this force into other forces, other component forces, if we use a little bit of trigonometry. So in this case, that's extremely useful because the force that would carry this box down the plane is not this force. It's only a part of this force actually carries the box down the plane. And the part of this force that carries the box down the plane is in blue. It's called F para. It means it's parallel to the plane. So that should make a lot of sense. Only the part of the weight which is parallel to the plane is going to take the box down the plane. So only F para causes motion parallel to the plane. And that is going to be highlighted in this equation, which I'll speak a little bit more about in a few moments. But there is another component. So we have the weight, which always points down towards the center of the Earth. We have the component of weight, F para, which would carry the object down the plane. And we have another component, which is F perp, which is the component of the weight which is perpendicular to the plane. F perp will always be equal in size, but opposite in direction to Fn, the normal force. And since F perp and Fn are equal in magnitude but opposite in direction, they'll cancel each other, and that basically means that object, the box M, it has no ability to move either through the plane or above the plane, so there's no motion there. If the Regents were to ask you about the value for normal force or the value for F perp, we could use this equation. So assuming that F perp and Fn are equal, then both of them would also be found using the equation Fg cosine theta. And remember from the previous lesson, actually, that Fg is equal to mg in all cases. So we can also take a look at this Fg and Fg cosine theta and replace it with mg. So these equations, Fg cosine theta and mg cosine theta, are almost always useless, but they would give you values for F perp and Fn. And again, the reason why they're useless is that F perp and Fn will always be equal to each other, and the object cannot move in either one of those directions. So it's a strictly theoretical question about the value of F perp and the value of Fn. Now, I would like to contrast that with an extremely useful equation, which is the values for F para and Ff. So I would like to point out that F para is the only component of the object's weight which would actually carry the box down the plane. So F para is an extremely useful value to find because it's going to tell you the acceleration down the plane as well. So starting from there, F para is sometimes equal to Ff, and that Ff is frictional force. And the only times when you can assume that F para is equal to frictional force is when you see some very specific language in the question. And that language is here. It says that F para is equal to the frictional force when one of two things is stated, either that the acceleration is 0 or that the velocity is constant. I'm going to circle that now to highlight its extreme importance. And therefore, we can state that F para is in fact equal to Ff, which would simply go the opposite direction, but it would be equal in size, just opposite in direction. So F para is equal to Ff if we have an acceleration of 0 meters per second squared. Okay, so let me finish up explaining this equation. F para is sometimes equal to Ff. Okay, so now you know that you can say that F para is equal to this stuff, and sometimes you can say that Ff is equal to this stuff. That sometimes is dependent on acceleration being 0. But F para is always equal to this stuff. And it would just say that Fg sine theta is going to give you the value for para. you can see that it's very similar to this equation, except that instead of cosine, we're using sine. So I'm essentially saying that the weight, Fg, which is this value, the weight multiplied by sine of the angle theta, which is that angle, is going to give you the value for F para. So you can find this value if you take this value and multiply it by sine of this value. One more time. This value can be found by multiplying this value by the sine of this value. And additionally, Fg is equal to mg, so that means if Fg sine theta gives you F para, then mg sine theta gives you F para as well. And one more time, there are cases when you can use either of these equations to solve for Ff, but the frictional force, but you have to have an acceleration of 0 or you have to have constant speed. So I'm going to treat this slide more or less conceptually. What we're going to discuss on this slide is an object on an inclined plane, but we are changing theta. The easiest way to deal with this is to think about what happens when we increase theta. And what I would say is that if you make theta larger, you should notice a reduction in F perp and an increase in F para. I'll show you that in a diagram now. So I apologize for my really hideous diagram, and it is a bit smaller than the previous one, but what I tried to show well was that the angle theta is increasing from let's say a 20 or 30 degree angle to a, let's say, 70 or 80 degree angle. So theta is a lot larger. I did show a value here, which is my FF, which is going straight down towards the center of the Earth, and I'm trying to evaluate how that would affect F perp and F para. So F perp is perpendicular to the surface of the plane. That's why I drew it at a right angle to the plane. And I also realized it was a component, so I only drew it this far because I knew I needed a parallel component to connect to the tip of the weight vector. So here's my F perp. It's actually, if you look at it visually versus this F perp, you can see the F perp has gotten a lot smaller. And also F para, especially if you evaluate it against this F para, my value for F para is a lot longer. Now remember, F perp has an analog, which is Fn, which would be equal in size and opposite in direction to F perp. And Fn also has a direct relationship to the amount of friction that the box will experience. You probably remember that Ff, the frictional force, is equal to the coefficient of friction for the two surfaces multiplied by normal force. So my point here is that as the angle goes from a small angle to a large angle, you're going to notice that Fn gets smaller. And the reason for that is because F perp is getting smaller, and they're equal and opposite. So F perp has begun to shrink. Fn is going to shrink in kind. And that means that you're going to be getting a smaller value for Fn as the angle for theta increases. And if Fn is getting smaller, keep in mind that the coefficient of kinetic friction remains the same for those two surfaces. That also means by a direct relationship that Ff, the frictional force, is also going to decrease. Therefore, as the angle theta increases, the normal force is decreasing, the frictional force will decrease via this equation, and that means one very important thing, which is that the acceleration of the object down the plane would be larger. So you get more acceleration of the object down the plane if you increase the angle theta. So I think one of the interesting things on this slide is that that's something that you know intuitively. Like that's something that makes sense. You know that if you increase the angle of the plane, that the object would slide at a faster rate. and its acceleration would be more, but this is the physical reason why. And so we have finally made it to the pair up. You don't need to copy these questions down. I've already made photocopies for you, and you'll include them right after the do now questions that you copied down and the aim on that class worksheet. So you'll include them right after that in your binder. We'll do them in class. More pair up questions, I'll have these for you as well. But your summary questions, I need you to copy these down on that same piece of paper that you copied down the do now questions. In which direction does friction act? A 10 kilogram block of each. How does one solve for the coefficient of friction? What's the component of an object's weight? And according to your reference table. So copy all of those questions down, and we will do these in class the day that you see me after having done these notes. Thank you for watching, and have a wonderful evening.